Okay, we are in Isokinetics, and now we are in part 2 of this series of lectures. And in part 1, we derived this equation. I'm going to rewrite it right here. T sub q, the torque due to the quadriceps, is equal to the resistance torques. In this case, the torque due to gravity acting on the foot-leg system, and the torque due to the machine providing resistance. So remember, collectively, this is resistance torque, and this is what the muscle is doing. Now, what's really important about this equation, I stated, the equality sign here is important. What the muscle is doing is the same as the resistance. What this means is no matter how hard the muscle or how much torque the muscle is generating, the machine will respond to match that torque so that the torques add up to 0. Okay, no matter how much muscle force is generated, the machine, in this case I'm using a machine, responds with the right amount of torque, right amount of force times moment arm of torque, so that angular acceleration is 0. That's isokinetics. Angular acceleration is 0 means velocity is constant. Okay, this is isokinetics. Now, just take a second and think about what this means. It means that no matter how hard the person pushes against the resistance arm of the machine, okay, this picture right here, no matter how hard the person pushes against that machine, the machine is going to respond with the right amount of force and therefore the right amount of torque so that angular acceleration is 0 and velocity is constant. This is the beauty of this machine, in that if I tell the person to push as hard as they possibly can throughout the entire range of motion, that machine will respond with the right amount of force, right amount of torque at any point of the range of motion. So this resistance is varying throughout the range of motion of knee extension, the example we're using here, so that it matches whatever this is, so that these all add up to 0 angular acceleration. Why is that important? Because we know that the amount of force a muscle can generate is partly a function of how long the muscle is. And so we know that during a range of motion, the muscle will be generating different amounts of force throughout the range of motion simply due to the length. For isokinetics, that doesn't matter. We're able to detect that because the machine is going to respond to no matter what the muscle is doing, so that the torques are equal. The resistance is the same as what's the motive force, or the force causing a rotation, or the torque causing rotation. And remember, this is what I'm measuring. And so by measuring this, I'm now able to detect how much torque the muscle can generate at any point in a range of motion. And that becomes really powerful. All right, so now in this presentation, in this part, I want to talk about some data that you would get back from this type of device. And I'm going to set this up a traditional way that you've done it with me before. And I'm going to put angular position. And really, I should be using radians here, okay? And I'm going to put time down here. And right below that, I'm going to put angular velocity in radians per second. Because remember, anytime we do things outside of PVA, we really should be using radians. And radians are unitless, and we just don't have to carry them forward when we do an analysis, a unit analysis. And then we have angular acceleration in radians per second squared. And I'm leaving room for positive, negative, and 0 indications there. And then I'm going to, similar to how we do PVA ground reaction force, but it's going to be a little bit different. I'm going to put torque here, and this would be in Newton meters, okay? And what I'm really interested in is the torque due to the quadriceps for this example that we're dealing with. Now, in an isokinetic machine, there's all different ways to set up the machine so we can test the strength of different muscles. In this case, I'm focusing in on the quadriceps simply because of the example that we're dealing with. Remember, I'm carrying forward the example from part 1. So make sure that you have watched part 1. In part 1, I drew this picture where we're looking at knee extension exercise. Okay, so we're going through knee extension. All right, so now if you remember, when we do angular kinematics, we always have to have a reference frame. And in linear kinetics, we typically say up is positive and what have you. But when we're dealing with angles, we have to remember that we need to describe what convention we're using to represent this angle here. And the convention that we typically use on the street is we say a fully extended knee is 180 degrees and flexion angles are decreasing. However, mathematically, it's actually easier if we call the anatomical position is 0 degrees and flexion angles are increasing. All right, and you'll see that in just a bit here. So that would mean that if the leg is, the lower extremity is fully extended knee, that'd be 0 degrees. And as I go through flexion, those angles are getting bigger. And as I go through extension, the angles are getting smaller. They're returning to 0. So let's think about this knee extension exercise. All right, knee extension exercise. In this position here, well, if I draw out the femur in this direction, in essence, this ends up being the angle that I'm interested in. And now hopefully you can see that as I come down here, if I go to this position here, that would be 90 degrees. And as I go through knee extension, that angle between that reference line and this marker is getting smaller. Okay, so I'm going to draw that here as starting up in this position and ending in this position. I'm not going to connect the dots just yet, okay? I'll do that in a second. So let's go down to angular velocity. Angular velocity is rate of change of position, and we know that if we look at the slope of the position versus time plot, that tells us everything we need to know about angular velocity. Now remember, we're in isokinetics. So what does that tell us about angular velocity? It tells us angular velocity is constant. So I'm going to draw a straight line. Now I'm also looking at knee extension. So let's make sure we have this. And using this reference frame, what that means is as I go through extension, the angles are getting smaller. So if I just try to connect those two dots, you can see that slope is going to be negative. That means extension velocities are going to be negative. Extension. The negative sign simply indicating that we're going through extension here. Now, I'm not going to start, here's my start and here's my end. I'm going to leave those blank right now, leave a little space there. I'm going to do the same thing here, where now I can connect those dots because angular velocity is constant. That means the rate of change of angular position has to be constant, which means that has to be a straight line. Constant velocity, straight line, okay? And I'm leaving the ends of this a little space here, okay? Now let's come down to the acceleration. I have constant velocity. What do I have? I have 0 acceleration, okay? Okay, angular acceleration is 0. This is isokinetics. Kinetics. Angular acceleration is 0. All right, so hopefully you're picking up on a subtle detail here. Is there something happening here? Well, if I start the person in zero velocity and I say, okay, go, and the person goes through knee extension, well, now I'm going to go from a zero velocity to whatever I set the machine for. In fact, I should probably put that here. I predetermine velocity, angular velocity, okay? I set the machine to allow only 20 degrees per second. I set the machine to allow only 60 degrees per second or 200, whatever the number is. That velocity number is telling the machine that no matter how hard the person pushes against the resistance arm, the machine is going to respond with the right amount of torque so the angular acceleration is zero. All right, so I preset that. I put that in the machine. And I know I said degrees per second because a lot of machines are set that way. But remember, once we go to 0 radians per second squared, it doesn't matter anyhow because we're going to end up with 0 torques. At the sum of torques will end up being 0. So, and the same thing at the end, I'm going to finish the knee extension and I'm going to stop the leg. I'm going to go back to 0. Well, now I've got accelerations that are either negative or positive. In reality, what I actually have are these funny little bumps at the end. So this is isokinetic range. This section and this section, not isokinetics. So if you're doing isokinetic testing, you do not want to look at the area of movement where there is acceleration because that's not isokinetics. But you have to recognize that you're starting at 0 velocity and going to some predetermined velocity. So there's going to be some period of time before and after that isokinetic period where the exercise is not isokinetic. This is also important, and this is for students who may have already used an isokinetic dynamometer, is that there can sometimes be a learning involved with how to do this contraction. And if you use this machine and the machine stutters along the way, or it sounds sort of like a machine gun, it just rattles, goes da 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 da. What that is telling us is that the machine is not operating at isokinetics and that it's starting, stopping, based upon what the person's doing. And those situations are not a good use of isokinetics. In fact, it does not represent isokinetics because the machine is starting and stopping. And usually that's a learning aspect of a subject. You do need to get used to how to do isokinetics. And especially when we start doing eccentric contractions on an isokinetic dynamometer. Okay, so this is the PVA for an isokinetic exercise. Well, now I'm going to draw out the torque due to the muscle. And it's not as simple as F equals ma, where we identify the acceleration and multiply by m. That's not the case here, because this equation is a little bit more complex because I have the resistance torque also varying as the muscle torque. But if I drew out the muscle torque, it probably would look something like this. And I should have left positive, 0, and negative regions for torque. I drew positive because here we are trying to go through, we are going through extension, okay? Oh, I just messed up, but that's okay. I just flipped my reference frame. Extension, yeah, okay. I messed up, but that's okay. Here we are representing a torque where it is trying, the muscle is trying to cause knee extension. All right, and so this is very characteristic of an isokinetic exercise. There's some subtleties in terms of maybe there's something happening over here depending on what speed I'm actually testing. Okay, and so now what I want to do is take this information and then transfer it over to another plot where we talk about joint powers. Okay, so let me do that. So let me put 2 here. I think I'm still okay, actually. All right, so now what I'm going to do is draw out only the angular velocity, radians per second, positive, 0, negative. And this is time. I'm only going to draw out the angular velocity, and I'm not going to concern myself with the the regions where we are not looking at isokinetic. I'm not concerned myself with the starting or the stopping of the movement. Yeah, I'm upside down, okay? And the reason why I'm upside down is I need to, I was saying one thing and I changed in my mind, so I'm actually going to go back and redraw this. But this is what we would see on the machine, where the machine may actually just switch everything to positive. Okay, so I'm going to take that off. I'm going to redraw. Okay, so now I'm going to draw just the angular velocity, positive, 0, negative, time, and the torque. I'm going to keep the muscle torque here versus time plot. And then right below that, I'm going to draw a new plot. And I'm going to put joint power down here. This is still watts, positive, 0, negative. Now, what's important about this is now this term, joint power, is specific to what amount of energy transfer, or how fast we're transferring energy about a specific joint. And when we do isokinetics, we're able to start looking at whether or not velocity is positive or negative, whether or not muscle torque is positive or negative, and what that means for joint power. Now, power, remember, is force times velocity. Then nothing's changed except we're going to use the equation power equals torque times angular velocity. Now, power is a scalar, meaning it's represented by magnitude only, but we know power will be positive or negative. And what we need to do is interpret that direction of the power value to mean either concentric or eccentric contraction, or muscle is being generated, or muscle is generating force to cause movement, whereas, or in an eccentric contraction, its muscle is contracting to resist a particular movement. So the direction of these elements ends up driving our interpretation of what power is. I'm not going to do it for isokinetics, because on one hand, what I draw here is different than what you see on the machine. The machine is always going to show velocities as being positive. And then the machine will ask you whether or not you want the velocity to be either an eccentric or a concentric velocity. Either is fine, okay? But from our math, we ultimately need to bear that out. So I'm not going to draw it at this point. But it would, in an eccentric contraction, the machine torque is still matching the muscle torque, but the machine is just getting movement going in a particular direction. Once that eccentric velocity is achieved, then that velocity is constant, angular acceleration is 0. We would multiply that by the torque value, and then we get a power value that's either going to be positive or negative, and then we interpret that positive or negative relative to the type of muscle contraction that's happening. Either it's concentric or it's eccentric. And it gets a little confusing here because sometimes the signs flip. If we're doing gait, or if we're even doing this type of task, a positive sign can mean one thing sometimes, and sometimes it can mean something else. Sometimes it can mean concentric, sometimes it can mean eccentric. But in a subsequent presentation, I'll go through some different power versus time profiles for gait and also we'll do some for cycling and maybe a little bit for swimming, because now we're getting a little bit more information on swimming forces due to some of the technology that we have in the pool. So joint power will start telling us information about how the muscle is contracting, whether it's concentric or eccentrically. Torque is telling us what the muscle is trying to do, and the angular velocity is telling us what is actually happening. Either we're going through flexion, going through extension. We're going to talk about these as being extensor torques or flexor torques. And then this, we'll talk about concentric or eccentric contractions. Okay, I'm going to leave it at that for now, and I'll have another presentation to fill in some information about sport-specific joint powers. Okay, thanks.